Okay, so you can see the this thing slide now. We will do a real use case study, which is a student university data, which is available in the internet, and we'll be using the Statcraft, and I'll be using the Statcraft with R trial license. So it gives you the output like SPSS, and at the same time, it also gives you the R codes, so that if you have R Studio, you can run it in R Studio and get the same results. So before we start with the data set, let me actually just very briefly take you around to what exactly is statistical and hypothesis testing, which you already know, but a little bit of a rebrushing of the concepts is important before we do any data set analysis. So obviously, what is statistical analysis? You are collecting and analyzing a sample of data, and from that data, you are uncovering some data patterns, which will help you to predict what will happen, and it will help you to make some good scientific decisions. Now, the key word here is the data that you have. It is basically called a sample, and using sample, you do something which is called descriptive statistics. And in order to check something about the population, you have to actually infer about the population and predict about the population. If you're using statistical analysis and you want to know something about the population, you will do a hypothesis testing to check the population parameters, which is basically comparing the sample mean with the population mean and checking whether they are statistically similar or significantly different. Or if you want to do a little bit on the machine learning, where you are actually going towards actual prediction using prescriptive analytics, then you can actually use that sample data for as a learning data for supervised learning. Statistics, as you know, is part of two parts: descriptive and inferential. In inferential, we actually estimate about the population parameters based on the data that we have from the sample, and that we can only do when we clearly cut out a hypothesis which can be tested. So how do you go about doing it? First and foremost, you actually frame let's say a research hypothesis, any idea based on the literature, data, or whatever, and then you design a questionnaire, because it is all quantitative analysis. And that questionnaire, you actually go and visit the respondents, or you can send it through Google Forms over mail or WhatsApp, get their observations, and have at least more than 30 sample data to qualify for a good t-test, and then interpret that Likert data, which is on a scale of 1 to 5. So Likert data is basically, there is a difference of opinion whether it's a parametric or non-parametric. Actually, it is an ordinal data, because it is ranking the various questions and taking your opinion from highly dissatisfied to highly satisfied, and in between there is neutral. Highly dissatisfied, neutral, satisfied, highly satisfied. So you can rank it on 0 to 5 either way. Either highly satisfied is 5 or highly satisfied is 1 also, or 0 also. It will give you the same results, because anyway it is ordinal data. So based on that, you actually collect the scores, and then you convert the research hypothesis into something which is called statistical hypothesis, which is basically convert them into null and alternative hypothesis, which can be measured. But before you go to do any analysis, you first have to check the normality of data, whether the data is normally distributed or not. Because if the data is normally distributed, you will go for parametric test. If the data is not normally distributed, you will go for non-parametric test. You would have done a lot of parametric tests. There are 3 T tests. There is a Z test, and there are many Anova tests. 1 factor, 2 factor Anova when you are comparing the means. And also you do correlation. But when you look at the non-parametric test, which will usually be the case in many cases, in that case, you will go for the equivalent non-parametric test. So whether you are doing a coding-based analysis using R and Python, or you are using certain tools like Advanced Excel or SPSS or Statcraft, you should have those tests available to you. Then whether you are using parametric or non-parametric, you will check the p-value. And let's say you've taken a confidence interval of 95%, which is for mostly social projects, management projects, social science projects. At 95% confidence interval, the margin of error or threshold value or alpha is equal to 0.05 or 5%. So the p-value is more than 5% or 0.05 if you accept the null hypothesis. Otherwise, or you don't say accept null hypothesis, you say fail to accept fail to reject null hypothesis. Or if it is less than 0.05 p-value, you reject the null hypothesis, thereby implying that you are basically chosen the alternate hypothesis, which also happened to be your research hypothesis. Now, there is a lot of confusion about what exactly is this p-value. It is not the probability of selection of the null hypothesis. It is basically the probability of making a type 1 error. And what is exactly a type 1 error? Type 1 error is basically you reject null hypothesis when actually null hypothesis is true. So if the threshold margin is 5%, and if your actually p-value is more than 5%, that means you should not reject the null hypothesis. You will be making a greater type 1 error. Hence, the p-value is significant based on the confidence interval. So quickly going through this, null and alternate hypothesis both are opposite each other, but the fact is these are statistically measured, and you have to use a random sampling. Only then the p-value is relevant. P-value actually tells you that the sample that you have chosen and the results that you are getting is not by chance, but there is a likelihood that any other sample that you choose, you will get the same results, favoring null or otherwise. The statistical test that you always do is for null hypothesis, not alternate hypothesis. So you have the t-value. You also in hypothesis testing, there are 2 ways in which you can check the hypothesis, P and T. A t-value, when you calculate using a formula, gives you t calculated, and then you have the t tables with various degrees of confidence. You should know how to read a t table with degrees of confidence and degrees of confidence and alpha values. If the t calculated is less than t tabulated, you go for null value because t is lying, the calculated t value is lying in the null region in the bell-shaped curve. If the t calculated is more than t tabulated, then obviously it is lying in the rejection region, and you reject the null hypothesis. So you have two options. The tools, SPSS and Statcraft and all, and advanced Excel, they give you T as well as P. So you can actually compare the T calculated with T tabulated, and if T calculated is less than T tabulated, go for null. And or alternatively, you can simply check the P value. If P is more than 0.05, go for null, provided it's a 5% is the threshold value. The key importance to be noted is many people, when they do this test, they simply go with the T test or Anova test. They forget that there is a very important parameter called parametric non-parametric test, because you have to first check the normality of data. Only then you have to go for parametric and non-parametric test. Here I will tell you how to check the parametric and non-parametric test using normality of data, because your entire statistical test depends on whether it's parametric or non-parametric. There will be equivalent of T test in non-parametric, equivalent test of non-parametric in Anova family also, but the formulas are different. So you can get different results. If suppose it's a non-parametric data and you do a parametric test on that, you may get a different result. So this is, I think, a very, very important part, checking the normality. And more important, the underlying principle is that you should be a random sample. From the target population, you actually have to select a sample which is random. And all the tests you are doing on the random sample that you choose. Sample size should be more than 30 for qualifying for a good t-test results. It can be less than 30 also, but ideally it should be more than 30. So choose your number of respondents to at least 100, and then only you will get at least 40-50 responses. Then you have to clean the null and errors from the data, and then you actually have to get the data out of the Likert scale, and then you go for the parametric and all. We'll see using a real data. Very simple how a normal distribution curve looks like. A perfectly bell-shaped curve. Mean, mode, median are at the center. They are basically coinciding, and it gives you the spread of 1 standard deviation, 2 standard deviation, 3 standard deviation to the right and left, called 1 sigma, 2 sigma, 3 sigma. Why we keep saying that? Why we keep saying that normal distribution is important is for the simple reason that not only it has the mean, mode, median all at the same level, but 68% of the data lies between plus and minus 1 sigma. 95.5% of the data lies between plus and minus 2 standard deviation, and 99.5% of the data lies between plus and minus 3 standard deviations, and the rest all are outliers. So it is very easy to predict a data when you know that it is a normally distributed. So first of all, you check the sample data, and from the sample data, you see the pattern of the data, whether it's normally distributed or not. There are two ways of doing it. One is a graphical way of checking it out, which is a histogram. Also, there's a quantile plot, which I'll tell you today. And then there is, of course, the test like Shapiro will test for normality, which is a checking the alternate and null hypothesis. Most of the things, I mean, normal distribution has been there for many, many years, more than 200 years now. Most of the things which are created by God, follow a normal distribution. Your heights, weights, blood pressure, IQ levels, all are normally distributed. So basically, you can see that you can check the heights or weights. It will be normally distributed. But not everything in the world is normally distributed. Man created data is never normally distributed. If I check the salary level of a particular company in manufacturing sector and assume that the data is normally distributed in the entire manufacturing sector, that may not be true. Or I can do some other results. I can actually check the marks of a particular sample and assume that the entire university marks will be normally distributed. That may not be true. When you check at the normality curve, this is what we have already spoken. 68.3% data lies between plus minus 1 standard deviation. 95.5 between 2 and 99.9, 99.7 between the 3 standard deviation. Rest is all outlier. One quick way of checking a normal data out of a sample is that check the histogram. It is a univariate plot. Advanced Excel gives you instant results on histogram, and connect the center points of all the bins and check the shape of the curve. Whether it is a perfectly well shaped, it is a left skewed or right skewed, you will get the results. Left skewed is when the mean is less than the median. Right skew is when the mean is more than the median. Now, look at this slide carefully. We have to check first the normality of data. And one way of checking the normality of data, of course, we are doing descriptive stats because everything is from the sample data only. Shapiro-Wilk test is very, very commonly used. What does the Shapiro-Wilk test do? Tells you? It is the test for hypothesis. The null hypothesis tests that data is normally distributed. Alternate hypothesis tells that data is not normally distributed. Similarly, there's a Kolmogorov-Smirnov test. What is the difference between Shapiro-Wilk and Kolmogorov-Smirnov test? When the data size sample is large, we go for Kolmogorov-Smirnov test. Typically, when the sample size is 200 or above. But when the sample size is small, we actually go for Shapiro-Wilk test. Then there are other tests like for the normality for alternate and null, SCS test, KU test, SCK test. But remember one thing, null hypothesis is data is normal, alternate hypothesis is data is not normal. We are checking at a confidence interval 95%, which is in our hands. So based on whether the p-value is more than 0.05 or not, you settle for null or not. If p-value is more than 0.05, then it is a normally distributed data, otherwise not. Quickly, you can do a graphical test also. And these are the various tests which are mentioned here. But one of the tests which we can do is Q and Q plot apart from histogram. And Q and Q plot is much more accurate. Histogram actually will give you a very approximate shape. Q and Q is a quantile plot. We'll see what that quantile plot is all about. All the data points, if they lie in a straight line, it is normally distributed in QQ plot, otherwise it is not. Data analysis, apart from slightly different from inferential statistics, is basically when you start analyzing the data patterns, That part is common between hypothesis and predictive analytics. First, you analyze the data, clean the data, and then either you go for hypothesis testing, which is estimating about the population, or you go for a machine learning algorithm, which actually gives you a prediction either on a classification or on a regression basis. Classification is whether the loan is passed or not, binary or maybe 3 states. Predictive analytics can be done through statistical analytics. You are using the historical data and you are doing some statistical algorithm and predicting something. Regression is a very good example of predictive analytics. It will give you a continuous output data. Same you can do for logistic regression, which gives you binary output of a continuous data. Prescriptive analytics is mostly on the machine learning side, where it actually not only gives you the answer, but tells you what you should be doing. So that is a very complex algorithm. There are many machine learning algorithms which are used, which you have already gone through many times. So when we come to prescriptive analytics, we actually step out of statistical analysis and go for machine learning, deep learning algorithms. Before that, we do something which is called exploratory data analysis or EDA. People who are using Python, they must be very conversant with EDA. You actually find the null values, clean the data, make the data good. If there are null values or missing values, either you replace them with nothing, some delete those data if it is small, or replace them with the, mostly it is replaced by mean, sometimes median. Otherwise, it will give you error in results. Quickly summing up, descriptive and inferential. But more important that it's parametric and non-parametric. Parametric, you do 2 tests, comparison and relationship. Comparison, you get the groups, 2 groups and 3 groups based on the grouping variable. Relationship, you simply take 2 continuous variable and establish a relationship, whether it's correlation. If it is showing a strong correlation, then you go for regression. Strong correlation is something like more than 0.7 or 0.6 onwards. Again, you have parametric, non-parametric data for correlation. For parametric, you have Spearman's correlation. Your Carl Pearson correlation. Non-parametric, you have Pearson correlation. Comparison, how you find the comparison, how many groups. If the grouping variable is true, suppose you are doing on gender, then male and female. And then the testing variable is that continuous data, whatever you are testing on that male and female. If the grouping variable is 3, based on the race, then you are basically taking 3 data, continuous data on those 3 grouping variables, and then you are doing an Anova test. But I think this will be very clear when we do a real life use case study. Similarly, we have non-parametric test when the data is not normal, and equivalent of independent sample t-test is Mann-Whitney U-test. Equivalent of one sample t-test is Wilcoxon rank test. In fact, there is a Wilcoxon sum test also, which can be used for independent sample t-test. And then when you go for more than 2 groups, which is Anova test, single factor Anova, there is no interaction here. Then you have the Crucial-Wallis test for data which is non-parametric. So you have these tests which are there, which you have not done. So this will be doing this time. So before that, I will tell you the data which I'll be using. It is readily available on the internet. And as you can see the data here, this is 11 features from ID, gender, race, SCS, SCS type, program, read, write, math, science, social studies. 11 categories. Now, first of all, most important, scales of measurement. What scale of measurement are these? The ID is of no importance to us. It is a purely a categorical data. Nominal data it is just identifies a person. We don't do any analysis by the person name in any analysis. So we ignore this column altogether. Then there is gender. It will be used for grouping variable, male and female, two groups. Then there is a race. There's a white race, African American. I'll just increase this so it will be clearer. On the race side, it says white American, African American, and Hispanic. Three groups. So if I arrange the data on these three groups, it will be a Anova test. Then socio-economic status, SCS. There are three groups: low, middle, high. Again, Anova test. Then school type, public and private, two groups, T-test. Program, what program you have enrolled? General, vocational, and academic. Three groups again, Anova test. Now, these are nothing but categorical variables from B to F. These categorical variables are used in grouping variables for T and Anova test. For testing variables, we will be using the continuous data. We have another 5 testing data from read, write, math, science, and social studies. Now, what is this data about? This is, let's say, let me scroll down this data. This is around 200 data sets. So reasonably good data set. It's a sample, obviously, from a university, and they have actually done a survey and they have found out the gender, race, social economic status, school type, and what was your educational background before you enrolled in an university, and then it has actually tested the students' scores in reading, writing, mathematics, science, and social studies. It is apparent that this course could be out of 100. It looks like it is a score out of 100. And then we actually get down to various hypotheses. So when you do a survey, this can also be a survey. You can do a survey, ask them various questions, like, start with certain grouping questions. What is your gender? What is your race? What is your social economic status? And you give them 2 options or 3 options. What school you went into, public or private, and what kind of studies you are enrolled in, academic, vocational, or general. So there the respondent will just tick mark. That is not a Likert scale question. That is just a tick mark question for the grouping variables. Then you actually get down to their scores. Obviously, when you get down the scores, it is not a Likert scale. You simply note down their scores, whatever it is. But equivalent, you can also ask them certain opinion-oriented questions from highly dissatisfied to satisfied, and then you can get the scores from 0 to 1 to 5. So this is the data. Now, let me start this tool called Statcraft. You can actually use any tool. It need not be one tool. Various tools are giving various ease of use to people. There are two types of tools which people can use. People who are okay on programming side can go for Python and R. People who are wary of programming can go to ready to use tools like SPSS, Statcraft, Advanced Excel. Each has its own GUI and ease of interface, and it depends on the comfort level of people. But they all essentially will give you the p-value, which will be the same because the formulas are same. So it is a web-based tool, and it is a Statcraft R. So it will also give you the R codes as output, along with the output, which resembles like a SPSS output only. So there'll be username, there's a password, and here I have taken a trial license from them. Fiction. So when you open the Statcraft, it's a web-based software. It is everything is on the web, everything is in the cloud. All the data is always saved in the cloud. You go to this view, you will get the tables, data, metadata, and output. Table is the data that you will be uploading. Data is basically all the previous data that you uploaded. Metadata is the scales of measurement of those data. Output, all the output results you're getting. Models is all the model that you get. So if you're used to a screen of SPSS, then you know that there are two screens in SPSS, which is not there in Excel. One is the data view and the other is the variable view. In Statcraft, you just have one table, which is variable and data both. There are two parts of a data. The data can be constant and the data can be variable. It can take different values of the, it can take different values. So I go to this three buttons here, which is used in the menu, and I start with something called data, and I will be importing the data. I have to give some data name here. So I will give data. I'll give a name, university data. If it is already there, it will not allow. Since it is not there, it will allow. Table description, I'll give student marks. I'll upload the data. This is the university data set that I have uploaded. So it already gives you the various scales of measurement. So whatever is the red, you see that there is something called OK here. I can't use this OK right now because I have to, there is something which is in the red is not allowed. So they are not allowing me to use the rename variable ID. They must be using for something else. I just make it ID1. They're allowed. Similarly, they will not use it for general name like read and write, which was used in their other operations. I just use read and write 1. And now OK is operational. I'll say OK. So now I can go and look at my view. Tables. This is the table. All the previous data set. This is the data that I have just uploaded. And this is the metadata. The measurements. Let me come to the data. So this is the same data which was there in the Excel sheet. 11 categories of data, and out of this 5 are categorical variables and 5 are ratio variables, which is a continuous data. Now, let me ask you at this stage, looking at this data, how many possible hypotheses can I get? This is a sample data. How many possible hypotheses is possible? At this stage, since it is a real use case study, it is difficult to answer this question. But let us explore this and you see how many hypotheses is possible. But before that, I will do something which is called test for normality. And test for normality is always done on a univariate data. Univariate data is my read, write, math, science, and social studies marks. So I do test for normality. I will go for Shapiro will test. It was the usefulness of such user interface GUI tools is that it gives you instant outputs. I will use the analysis Shapiro will test of normality, or I can just see normality test. This is the analysis because output will store as there. On the variable part, I can check the various numeric variables or the ratio variables, which are these one, read, write. So this tool will only allow me to pick up numeric variables. ID1 is also a numeric variable, but it is of no significance in this test. It will not allow me to pick up gender, race, SES. You can see from the samples because these are categorical variable. I need a continuous variable for normality test. So let me start with read one. When I take here read one, it gives me OK. And look at it, immediately gives you the data output. And if you have been using something like SPSS, you will get a similar output window, box kind of results. And one thing you can see, you can also cut and paste on these things and paste it wherever in your report or whatever work file. It gives you the R code also. Shapiro test, Shapiro.test, read one. Read one is the file. So it gives you the output of the output as R test, R code also, which you can put on the R studio to get the same output. But more important than that, it gives you the p-value. The p-value for read test is 0.005. 0.0055. Remember our test for normality or 95% confidence interval. H0 or null hypothesis is data is normal. HA or alternate hypothesis is that data is not normal. P is 0.005, so obviously it is less than 0.05, which says that the data is not normal. So when it comes to data, when it comes to read, we can simply say that the data is not normal. Okay. Now, similarly, I will do something for, now I will read this read and now say write. Let me check normality test for write data. Write data is 9.86 into 10 to the power of -7, almost 0. Again, it is a not normal data because it is less than 0.05. It gives you so instant result. So the output will be one after the other. You can always cut and paste. I will again go for another data now, which is mathematics score. Now, since you are conversant with R and Python, imagine the type of time it takes for doing these tests in coding kind of. You'll get the same output, either of the platforms you use. Now, when I'm using this mathematical test, I'm getting 0.002. Again, it is not normal because it is less than 0.05. P is less than 0.05. The data is not normally distributed. So I will again go. This time I have gone the read, write, maths. I will take science and say OK. 0.03. It's still less than 0.05. Again, the data is not normal. Less than 0.05. Again, I go to normality test, do my last test of social studies. data. These are all univariate data. Again, it is very, very small, 0.000. So all my data is not normal. You can assume that because Shapiro will test is very conclusive because I am checking the p-values. I am not only checking the histogram. I can say that the population from which this data is derived is not normally distributed. So this is, and you can just scroll up the screen and you get all this Shapiro test, all these 5 scores. All of them is less than 0.05. So far, so good. There is another way of testing, which is a QQ plot and histogram. So let me basically just show the QQ plot. Again, go to the main menu, pick graphics, come down, you have scatter plot, bar plot, all these things. Lastly, you will have QQ plot, which is quantile plot. Click on quantile plot. So I'll just say QQ, chart title, QQ for normality. Variable, I'll pick up read, check the QQ plot, quantile plot. So this is the test for normality, very foolproof test using graphical methods. Now, if you see that all the data of read should lie on the single line, this loop line. There are 2 axes to this: theoretical quantiles and sample quantiles. And if the data is not lying on this line, then it is not normal distributed. So you can see that the data is not lying on this line. This is another quick way. But you know, whether you do this or whether you do this, time requires the same, but at least you should know. There are certain tools where maybe in Python using CBOM, the graphical part is very easy. Just one line code and you get everything. I do a right QQ normality. This is the right QQ normality. Again, you see a lot of the plots are lying outside the line. If they all lie on the same line, it is normally distributed, otherwise it is not. Just to get you with familiarity, how you do it, maths hardly takes 3 seconds on this test. Again, you see the data lying outside, not normally distributed. Math scores are not normally distributed. QQ plot, science, again data outside the line, not normally distributed. Last one, I'm getting the same result as I got on Shapiro test. Social studies, again data outside the curve, outside the line. So what we have concluded is whether I do a Shapiro test for alternate and null hypothesis or I do a quantile plot. All my 5 data, read, write scores, science scores, social studies scores, and math scores, they are not normal. Now, the first part is over, that this is not normal data. Now let me start with my hypothesis testing. For hypothesis testing, I'll say compare groups. I see t-test, I see Anova, I see non-parametric test. So obviously, I'll simply go for the non-parametric test. Usually people go for parametric test, but now I test the normality test. I'll go for non-parametric test. So when I go for non-parametric test, let me just have a look at the data. I will now take the first grouping variable gender. Now this grouping variable gender has 2 categories, male and female. And I have 5 scores All these are testing variables. And if I take gender as a grouping variable, then I can have one hypothesis regarding the read scores, which is genders have no impact on the reading scores. Null hypothesis. Alternate hypothesis. There's a significant impact of gender on the reading scores. I don't know, it could be more, it could be less, so it can be two-tailed test. If a researcher is very, very clear, he can go for a directional hypothesis. He can actually go for a single tail, which says that it is more. He can go for left tail, right tail or left tail, it is less. But mostly people will go for bi-directional because they are not sure. The reading score could be more or less for males and females. Null will say the reading score is same for male and female. And whenever I'm doing this hypothesis, it is not for the sample, it is for the population. I'm comparing the sample mean with that of the assumed population mean, and the p-value gives me that answer. Now, I can have 5 hypotheses out of gender only. Read, write, math, science, and 5 hypotheses out of gender. So let us see. Compare mean. Obviously, t-test will give me one sample, third sample, independent sample. Anova will give me one way Anova, two way Anova. I'm straight away going for non-parametric tests. Now, when I go for non-parametric test, there is a two test which is there, which is a Wilcoxon test. There's a Crystal-Wallis test. Crystal-Wallis test is basically for this thing. Crystal-Wallis test is for Anova. Now, I'm basically, when I am doing a gender test, there are two groups, male and females. Whenever there are two groups, we go for an independent sample t-test. So first of all, let me assume that this is a parametric data and then do the independent sample t-test, assuming that it was parametric data. But even before doing that, there is a test for testing whether the data, if it is an independent samples, two independent samples, they may be coming from different population, or they may come from same population. I want to test whether there is a homogeneity or not, whether they same variant or different variants. There are two tests in advanced Excel. Independent sample test, assuming equal variance or unequal variance. So there is a F test or the Levin test, which tests the F scores and V value, where again the H naught null says that there is homogeneity in data. There is no variance, equal variance. Alternate is there is no equal variance, there are different variants. So the T test gives you two different formulas for that. Let me check whether it is there or not. So here I don't see any Levin test which is there. Levin test is not here. So I will simply go for T test, assuming that it is a normally distributed data, and go for independent sample T test. I just write the analysis ITT. Variable I will take read. First hypothesis. Gender impact on read. Whether it's same or it is significantly different. So here on the factor, I will pick up gender. When it comes to gender, it gives me to give a number to that. I can actually go to the metadata and define my gender, male 1, female 0, or female 1 or male 0. It has to be a number. It can be any number. So here I define the number. I pick up female, and here I pick up male, or I can pick up anything. The moment I've done that, there are two levels of the gender. So the software has given appropriate number 0110. I press OK. So this is what there's a Levin test also accompanies that. In fact, whenever I do independent sample test, it automatically gives me a Levin test of homogeneity. Levin test was actually started by Levin in 1960, It gives you a F value. You can go to the F tables and check the F value because it's the F tablet calculated value. And the degrees of freedom is 198 because it is basically total data is 200. Now it also gives you a P value, and the P value is 0.50. In fact, it actually doesn't give you a P value. It actually gives you the value of the F from the F tables itself. So the F calculated is less than F tabulated. When the F calculated is less than F tabulated, it actually goes for supporting of null hypothesis. You can also go to advanced Excel, and there is a F test in advanced Excel data analysis tab. It's a plugin, and then it gives you the P value. It gives you the P as well as F value, but it is only required to do independent sample t-test. Now, when we do the independent sample t-test, my P value is coming 0.455. Now, 0.455 is obviously greater than 0.05. It also gives you the T value of 7.748. There is nothing negative T. And you can actually fill the T table at degrees of freedom 198 to find the actual tabulated T value at 95% confidence. And here you will find that the T calculated is less than T tabulated. Go for null. The same for P value 0.455, much more than 0.05. Null. Null means there is no difference in the read scores between male and female. Now, just for the sake of doing it, and in Python and all, it would have taken ages to arrive at this results. I did a simple parametric t-test, and I can go now for a non-parametric t-test, which is a Wilcoxon test. There are two Wilcoxon tests. One is a Wilcoxon sum test. Wilcoxon sum test is a non-parametric test for independent two samples. And Wilcoxon signed t-test, signed rank test is for one sample t-test. Let me go for Wilcoxon. I'll just say non-para variable read and variable. So this Wilcoxon test, if it is asking two variables, that means it is a paired sample t-test Wilcoxon. It is a paired sample t-test Wilcoxon. So I can't do this because I'm just doing independent sample t-test. Now, obviously, when I look at independent sample t-test, maybe I should have told you earlier, not all tests would be available in all the tools. SPSS, of course, would have everything. Now, when I see non-parametric tests here, the equivalent of independent sample t-test in non-parametric is called Mann-Whitney U-test. All separate words, all named after statistician. The non-parametric test for independent samples T is Mann-Whitney U-test. It is not here. It is very much there in spaces. Positives and negatives of all the tools. So I will now go for the second test, which is basically, now I can keep on doing this. It will hardly take 2 minutes. Independent sample t-test. I will again go for independent sample t-test. Just to tell you how quickly the results are obtained, because Mann-Whitney U-test is not there, so I'm assuming that the data is normal. Now, instead of read, I now take write. Okay. So here, remember when we did the read independent sample t-test, null was accepted because it was more than 0.05. Here you look at the p-value, it is 0.0002. It is less than 0.05, so null is rejected. Which means that my alternate hypothesis is correct, which says that there is a significant difference in the writing scores between male and female. In the read score, it was not, it was similar results. Here it is significantly different. So here I am going for alternate hypothesis as far as writing score is concerned. I am still on that gender grouping variable. So again, I go for grouping variable, T test, independent because man is not here. Instead of right, I do maths. See how easy within seconds it is giving me results. What is the math score? Wow, 0.68005. It is obviously null is accepted. Just like read, null is accepted. There is no difference in the mathematics score between males and females. Compare groups, t-test, independent sample t-test. Instead of gender, instead of maths, I'll take out maths and put science in gender. Yes, grouping variable. P is 0.07. Again, more than 0.05. Null is supported. For mathematics also, there is no difference in the scores of male and female. So the only where we found a difference and alternate was writing scores. Interesting results. But these are credible results. Nobody can doubt these results. I'll do the last test here, which is instead of science, social studies. Okay. P-value is 0.46, more than 0.05 again. No difference in the social studies scores. So I did 5 hypotheses, keeping gender as a grouping variable, and only in right alternate hypothesis was there. In all the rest 4 scores, null was accepted. So this will also tell you how clearly and with clarity your hypotheses are coming up, testable hypothesis, based on some survey that you have done. And how many different hypotheses you have done. For example, now come to race. Gender, we move to race as a grouping variable again. How many races are there? 3. White, African American, and Hispanic. When there are 3 groups, you will go for Anova test, single factor Anova, because there is no interaction between groups. That is my assumption. When there is an interaction, then you go for a 2-factor Anova. Right now, we're going for a single factor Anova. But and single factor Anova, I will go for straight away non-parametric tests, because all my read, write, social studies, math, science are all non-parametric data. Compare groups, I can go for Anova, 1 way Anova, 2 way Anova, but I know my data is not parametric. So I will go for non-parametric, and this time this test is available. This test is called Krusal-Wallis test. Named after the statistician Krusal-Wallis. I will do the Krusal-Wallis test, non-parametric test, because the data is not normally distributed. So it is Nova non-parametric. What is the variable? I have those same 5 variables. Read. What is the factor? Factor is race. 3 races. The Krusal-Wallis rank sum test has come up. And the p-value is very, very small. It's almost 0. Now, what does the null hypothesis here? Null hypothesis is there is no, all the 3 groups are similar read scores. The 3 races have similar read scores. That is null. What is alternative hypothesis? At least one of the groups is significantly different in having the read scores. At least one of the groups. Remember, the confusion is always there. Alternate is not all 3 groups are different. no, at least one of the groups is significantly different. My P is almost zero. Alternate hypothesis is supported, null is rejected. So when it comes to read score, I can actually say that at least one of the groups is different in having read scores. Similarly, quickly going down to this so that you get familiarity with this test. I again go to non-parametric, Krusal-Wallis, replace the read now, take out the read, now take write. Grouping variable is race. You also observe that in each of this output, the equivalent R code is also coming. If you have R Studio, you can simply type this Krusal.test, you will get the same results. The R code is coming. P values again very low. Again, null is rejected. At least one of the groups is a significantly different right scores. Again, non-parametric, Krusal-Wallis. Actually, don't do too many Anova tests. Where people actually keep on doing the t-test. See, the same data is giving you another 5 hypotheses are coming in. Match. Same results, at least one of the group is significantly different regarding the match score. When you take race as the groups. Krusal-Wallis again. I take out match and put science now. Again, alternate hypothesis, null is rejected. At least one of the group has significant scores. Last test, non-parametric, Krusal-Wallis, instead of science, I take social studies. Okay. P value is 0.02. It's less than 0.05 again. So remember, the lower the P value, the more significant is your alternate hypothesis. So again, one of the groups is significantly different regarding race. So when I look at race, I see that the scores are significantly different. Race is an impacting factor on the scores. Now, I have already done 10 hypotheses, 5 on gender, 5 on race. The grouping variable or the categorical variable only tells me whether it's a t-test or Anova, 2 or 3 groups. The number of testing variables gives me the number of hypotheses. Because there are 5 testing variables, for every group test, I can have 5 hypotheses. I go to the data again. I go to socio-economic status, SES. What is the socio-economic background through which people have come up to the university? I clearly see that there are 3 groups: low income, middle income, and high income. Clearly, there is no rocket science. Go for Anova. I already know that read, write, math, science, social studies, they all are non-parametric tests. So the non-normal data. So go to compare scores, non-parametric, Krusal-Wallis. Now, instead of factor here, I will replace the factor. Then I will choose socio-economic status. And let me start with the reads first. It will take very microseconds now, this kind of test. I am doing another 5 hypotheses on socio-economic status. Krusal-Wallis test, because there are 3 groups in socio-economic. Alternate hypothesis, and that is okay to some extent because the economic background makes an impact, but it cannot be a generic statement. It has to be statistically tested. P value is almost 0. Alternate hypothesis is accepted. Null is rejected. At least one of the groups is significantly different read scores in social economic status. Kurzweil test, I replace read by write and see what are the right source in social economic category. 0.003, again null is rejected. One of the groups is significant difference scores in socioeconomic status. Instead of right, I will go to the third one, mathematics. Maybe it will give me a separate results. In Kurzweil, no. Again, null is rejected. One of the groups is significantly different. Finish of the past two ones, which is maths replaced by science. Again, p-value is almost zero. Alternate hypothesis. Scores are one group has significant difference. Non-parametric last test Kurzweil. This is replaced by social studies. Okay. Same score. P-value is almost zero. One of the groups is different. So when I come to social economic status, I conclude that all the results from math, science, social studies, read and write, at least one group is significantly different. So social science, social economic status is making an impact. This is an impact. Data. I come to the school types. Rest all are very simple. Now tell me it's very easy. With school type, there's only two groups: public and private. You use public, there are private also. Two groups. So you know that what has to do. You have to do independent sample t-test. We will not do everything. We will just do a couple of them because they're all repetitive in nature. But when I go for non-parametric test, I don't have independent sample t-test. I don't have man-BTU test. So I will just do a couple of quick ones. I will just do compare test, t-test, independent sample t-test, assuming that the data is normal, though it is not. Let me do retest first, and the factor is school type. That was the factor, school type. Level 1, it automatically gives you, because the metadata is there, private school. Level 2, public school, so it has given them 0 and 1. P-value is 0.22. Good results, and you can see that the data also gives you the barcodes. So when I am taking the school types and I'm taking the read values, I find that there is no difference between public school and private school as far as the read scores are concerned. Null is supported clearly. Clearly, null is supported. Again, I am going for more 5 hypotheses. I've already tested 15 hypotheses in the simple data. 15 hypotheses. Independent sample t-test. School type. I replace the read as well as finish this entire thing. Right. Different results. 0.07. Again, null is supported. Same results. Null is p values are different now. Null is supported. Again, there is no difference in the right results as far as the school type is concerned. These are giving different results than socioeconomic, as you can see. Right, I replace. Maths I take. I'm curious whether null is supported everywhere or not. Again, null is supported. When it comes to math score, again there is no difference, whether you come from public school or private school. are interesting because the socioeconomic status gave me all alternate hypothesis true. This is giving me all null hypothesis to the school types. I replace the maths. I take the science score. Again, now more than 0.5, 0.36. No difference in science scores. All results are going towards null. When it is school types. I remove the school type. Sorry, I have to do the school type. I have to do the last one. I remove the science here. And use the social studies. Private, public, you can choose either. Just the number they give. 0.170 non-supported. So when we see all the scores, including social studies, there is no significant, there is all read scores are similar whether you go from private or public school. 15 hypotheses already done. 1, 2, 3. 20 hypotheses done. We have already done 20 hypotheses. Total 25 hypotheses and more. So let me go to this program. General, vocational, academic. 3 groups. Grouping variable 3. But crucial values test because all the testing variables are tested non-parametric. Remove this social. I remove this SOST with read, variable with read, and factor SCS. I take the program. There are 3 programs in university. P value is very low, almost 0, which means that there is a significant difference in the read score depending on the program that you undertake in the university. What are the programs that you are? Because now it is going on alternate. What are the programs? I check the data. The program is general, vocational, and academic. So that means, suppose you enroll in general or vocational or academic, there will be a significant difference in the read score. It actually maybe depends on the program that you are enrolling. Because you know these scores are based on 2 things. One is your past academics, your past schooling, your past ethnic background, past economic background, also course that you are enrolled in the university. Again, crucial values test. I replace the read. One thing you keep doing it, you get used to it. Right. Alternate was supported in read. Alternate is again supported in write. There is a difference in the write source based on programs that you undertake. Crucial values test. Replace the write with maths. Okay. Again, alternate hypothesis. There is a significant difference in the score of maths, non-parametric, crucial values, maths, science, replace maths with science. Alternate hypothesis again. All are going towards rejection of null. That means it is that the program that you take in university makes a difference. It will be interesting because whenever you go to a university and they have this sample data with you, you can decide before you take admission what scores are important, and then you decide what branch you want to take. I'll take the last one, science and social studies. So far, alternate hypothesis was supported. Here also it is alternate hypothesis, knowledge is rejected. So when you look at the data, I've done 5 hypotheses in gender, T, 5 in race, crucial values, 5 in socioeconomic, crucial values, 5 in T, school types, T, and 5 in program, crucial values. 3 times I 3 crucial knowledge tests and 3 independent sample tests. Total 1, 2, 3, 4, 5, 25 hypotheses I have already tested. And I would say that from this data, this is pretty comprehensive type of statistics that I have done. Now let me slightly change gear and look at some other hypotheses that can be done. Which means that suppose I just want to check between the same people who have done read and write because the data is the same. Like first data, which is ID 70, he has scored 57 and he has scored 52. Now there is a professor who is teaching and he assumes that before he started teaching, they already had the read scores done. So they came to the university and appeared in an exam and the reading scores were taken. Now the professor started teaching them and based on that, he gave them a written exam, right scores. Now you want to see whether the scores are different or same. So now we are talking about the same sample tested twice before treatment, after treatment, which means before the tutorials with the professor, the read scores, after the tutorials, the write scores. And you also see whether they are significantly different, these two scores, or they are same. So we can, obviously data is normal, we know. Go to compare groups, non-parametric. Now I can do a Wilcoxon test. Because Wilcoxon test is a test which gives me paired sample t test equivalent. So non-parametric test, and here variable 1 is read and variable 2 is write. So it gives a pair, it is true or it is false. I'll say obviously it is a pair because I'm using the same sample, I'm changing the sample. You can't change the sample in paired. T is 0.36, which is more than 0.05, which is normal, which actually tells the professor that there is no significant difference in the read and write scores based on the treatment given. And what exactly is the treatment given? The treatment given is basically your teaching. The ordered hypothesis is accepted. Now,